Hello students, so this is a video regarding the topic term by term differentiation of Fourier series. So we know that if a function, any function which satisfies the Dirichlet conditions can be expressed as a Fourier series, and the Fourier series is in the form a0 by 2 summation to infinity. Okay, so Dirichlet conditions we have already discussed in earlier classes. You can go through those conditions. So now a thing is that if we differentiate this function, then we will get f dash x, and at the same time we should also differentiate in the right hand side. Okay, so suppose we will get some series in the right hand side. We have to differentiate inside the summation. We will get some series. So now point is that this series which will obtain after differentiation, that will be the Fourier series of this function after differentiation or not. Okay, so sometimes we can simply differentiate the function or that the Fourier series of that function to get the Fourier series of the function after differentiation, but sometimes we cannot. So we have to understand those conditions when we can differentiate a Fourier series term by term. We call it term by term differentiation because we are going to differentiate each term inside the summation. Okay, so now we have to understand at which conditions we can do this differentiation. And another thing is that what is its advantage. See, if you know the Fourier series of this function and if you know the Fourier series of this function after differentiation, in one step, single step, you can obtain the Fourier series of that function after differentiation. Means what I am trying to make you understood that suppose you know the Fourier series of fx is equal to x square with the defining interval minus pi to pi. You know the Fourier series. Now you have been asked to find the Fourier series of fx is equal to suppose twice x. Okay, so individually if you try to find the Fourier series for twice x, it will be lengthy. Okay, but if you know the Fourier series of x square and you have been asked to find the Fourier series of twice x, then you simply do the differentiation of that function and the right hand side, in the right hand side that series. The series after differentiation will give the Fourier series of that twice x. So in one step you can obtain the Fourier series of another function knowing the Fourier series of a function. Okay, so now thing is that we can do this differentiation only when the function satisfies some conditions. Those things we'll try to understand. So we'll now see one example where we cannot do term by term differentiation. So we can start with that simplest example fx is equal to x. Okay, so suppose this is a function which has been defined with the interval minus pi to pi. So now we know the Fourier series of this function, that is fx equal to x is equal n from 1 to infinity 2 minus 1 to the power n plus 1 n sine nx. Okay, so since it is a odd function in this defining interval, so definitely it is a sine series. Okay, that thing you know. So I have not done all these in between steps. I have simply written down the final Fourier series of this function. Now if you do the differentiation of this function, that will be f dash x, it will become 1. So in the right hand side also you have to do differentiation. So after differentiation you will obtain from 1 to infinity, this n will be cancelled because in numerator another n will come. So 2 1 to the power n plus 1 sin x become cos, sin nx becomes cos nx. Okay, now we can expand this series to some few terms. It will become cos x minus cos twice x plus cos thrice x. Before all odd terms, plus will come, and all even terms negative sign will come, cos 4x. Okay, now we can prove that this series which we have obtained in the right hand side is the not Fourier series of 1. Okay, idea means this is one example where we cannot do term by term differentiation. For that I have shown this example. Okay, but therefore this series, this is not the Fourier series of 1. Therefore it is not equal. We cannot do the term by term differentiation in this case. Okay, so that how we can prove that. See, Fourier series of 1, that is 1, no? Fourier series of 1 is 1 if you write the another these terms, an cos nx plus summation bn sin nx. So here bn and n both will become 0 because there will be no any alternating components, only dc component should be there. So definitely the series which is a cosine series here we have obtained, that is not a series of 1. Okay, so that can be also explained with another tool. So 1 minute. Okay, here I will write again this one, f dash x is equal to 1 is equal to 1 cos. Okay, so now see, this is the point. Now this is fx equal to x minus pi to pi x equal to 0. If it is the Fourier series of, this is the Fourier series of 1, then say this thing with this example also. Suppose x equal to 0, it is a point of continuity. Let us put this x equal to 0 in the right hand side and left hand side. So if you put in the left hand side, it will become 1 because f dash x equal to 1, and in the right hand side it will become 2 is was there. Okay, 1 minus 1 plus 1 minus 1, like this. So here if you see, in this relation, left hand side it is coming 1, and in the right hand side the series is converging to nowhere. It is not a convergent series, it is a divergent series. Here 1 minus 1 plus 1 minus 1, it is non-convergent. But in the left hand side we are getting 1. Okay, so this is not something acceptable. So simply at the end we can say that the function fx is equal to x, we know the Fourier series of this function, or we cannot do the differentiation of this function to get the Fourier series, uh, uh, to get the Fourier series of that function after differentiation. It is not acceptable here. Okay, so what is the problem? Why we cannot do the term by term differentiation in this case? What is the limitation of this function f x equal to x? Why we cannot do the term by term differentiation? That thing we'll try to understand. Okay, so if you draw the function, if you draw the function f dash x, fx equal to x, it is a linear plot, and if you do the periodic extension, okay, whatever we draw in Fourier series any function, we have to see that thing in terms of periodic extension. Okay, if you do the periodic extension, if you see at that point x equal to pi, x equal to thrice pi, there is a jump discontinuity, means there is a break. After periodic extension the function is not continuous. Okay, if you write the function fx, and if you write the function after periodic extension like this, so this function is not continuous. So that is the problem here. So see, function should be continuous after periodic extension, then only we can obtain a Fourier series of a function also after that differentiation also. Okay, so that thing, if you take the another example, another example. Suppose that example, if you take that fx is equal to x square minus pi to pi, there if you draw the function minus pi to pi, and after periodic extension it will be looking like this. So if you see, after periodic extension also there is no any discontinuity. Okay, so all this is a continuous function, means function after periodic extension is a continuous function. So in this situation, if this is the situation of a function, then we can do the term by term differentiation. Therefore I have given this example before, that if you know the Fourier series of x square, then you can know the Fourier series of twice x. You have to just do the differentiation in the both sides. Okay, but that is not, and that is not similar for the case of x, because x, if you do the periodic extension, it will not give a continuous function, periodic continuous function. Okay, so now point is that functions which are which are continuous after periodic extension, those functions can be uh, done term by term differentiation. So we can write the definition like this. Okay, this thing I can show you this thing, how we can obtain the Fourier series of fx from this. Okay, so fx is equal to x square minus pi to pi. Okay, so we know the Fourier series of this function is pi square 3 plus summation 1 to infinity 4 minus 1 to the power n square cos nx. Since it is a, if you see, it is a even function. Okay, therefore we are obtaining the cosine series here. So now if you, I have already told that after periodic extension it will be a continuous function, means periodic extension is a continuous, there is no any discontinuity. So we can do the term by term differentiation for this function. So definitely if you do the term per term differentiation, it will get twice x, then it will become 0, then inside the summation 1 to infinity it will become n 4 minus 1 to the power n plus 1, because 1 minus 1 is will come from this differentiation of cos n nx. Cos nx, it will become sin nx. Okay, so you can write this thing. So this, if you write x, this 2 will get cancelled. So here n 2 minus 1 to the power n plus 1 sin nx. See, you can obtain the Fourier series of x, and we know this is the Fourier series of x that I wrote earlier. Okay, so starting with the Fourier series of fx is equal to x square, for this function we can obtain the Fourier series of x. How it has happened? Because this fx is equal to x square, it is a continuous function after periodic extension also. Okay, so this is possible in this type of function. You can do the term by term differentiation. So now we can write the definition, means the conditions. Definitions means conditions under which we can do the term by term differentiation. That thing I will write down. So this can be applicable in many situations. Okay, there can be problem where you have to apply term by term differentiation. So the definition, you can write that if f dash fx and okay, 1 minute, if fx is a continuous function, okay, in the interval minus pi to pi. That can be also, here we are writing all these things in terms of angle. If you take the arbitrary function, that can be taken from minus L to L. Okay, that is there. So it's a continuous function with the interval, and f minus pi is equal to f pi. Okay, so see, if this condition will be given, then only we can say that after periodic extension the function will be continuous. Okay, and this is the case. uh, this is the case, uh, and also another condition is that this f dash x should be piecewise smooth. Okay, then we can obtain the Fourier series. Then we can obtain the Fourier series of this function. Definitely will obtain, and we can also obtain the Fourier series of f dash x. Okay, see, when we were talking about the Fourier series of fx, means we are talking about the converse Fourier series of fx, then we were talking about the conditions that fx should be piecewise smooth. F dash x is piecewise smooth means, fx is piecewise smooth means f dash x, f dash x is piecewise continuous. Okay, here when we are talking about the Fourier series of f dash x, that is the after differentiation of fx, here we have to say that this f dash x should be piecewise smooth on that defining interval, means f double dash x should be piecewise continuous. Okay, so this is the thing. So as per the definition, the function should be continuous in a defining interval. The function should be continuous means, if I will write a function like this, suppose I will draw one function, this is from minus pi to pi, and it is mentioning like this. So inside that interval itself this function is non-continuous, then directly we cannot say, we will say that this function cannot be term by term differentiated. Okay, so initial condition is that function should be continuous in a defining interval. It should be this one, but here it satisfies this first condition. In fx equal to x, it satisfies its first condition, but it does not satisfy the second condition. Okay, so initially the function should be continuous in the defining interval. Second condition is that this is the second condition, and this is also condition of that even function. Okay, so means if this is the condition, then only if you do the periodic extension, then you will have a continuous function after periodic extension. Okay, and third condition is that f dash x, because we are getting the Fourier series after differentiation of fx, therefore f dash x should be piecewise smooth. When we talk about the Fourier series of fx only, then we say that f should be piecewise smooth. Okay, now when we talk about the Fourier series of f dash x after the differentiation of fx, then f dash x should be piecewise smooth. So that is the condition. So under these conditions we can do the term by term differentiation of a Fourier series. So here we can talk about the term by term differentiation of sine series and term by term differentiation of cosine series also. So in the later class, later videos, I will discuss regarding that, and I will also do some problem or examples. We'll discuss some examples related to this topic. Okay, so if you are getting any problem, you can write me in the comment section, and thank you very much.